Hello and welcome to this virtual workshop on multimodal capabilities in SAP HANA Cloud. My name is Markus Fath. I will be the speaker for the first half of this workshop. With me are my dear colleagues, Christoph Morgen, who will be running the second half of this workshop, and Shabana Samsudheen, Matthias Kemeter, and Daniel Dukes are also online. They're monitoring the chat and answering questions. Okay, here's what we want to do. We want to cover a couple of capabilities provided by SAP HANA Cloud, mainly related to the areas of spatial data, graph processing, and predictive analysis. This is a workshop. The way we handle that is that we will walk you through the exercises. So this will be a presentation of code and explanation. However, for sure, the data as well as the code and additional explanations is available online on GitHub. So if you want to run the exercises yourself or take a deeper look at certain code snippets, you can do so afterwards. The recording of that session will, of course, also be available afterwards. I think that usually takes 2 to 3 days until that recording is there. So you kind of have a reference or documentation that can help you to understand more detailed parts of that code. If you want to run the exercises on your own, what you need is HANA Cloud System. So if you're familiar with the trial version of SAP HANA Cloud, you can do most parts of the exercises with the trial version. However, for certain parts of the exercises, mainly the ones related to the SAP HANA document store and the predictive analysis library, so the machine learning part of this workshop, you would need a full SAP HANA Cloud system. If you don't have access to that, but still would like very much to do these exercises, contact us afterwards, and we can provide you access to our demo system, which we keep on running for at least a couple of days. Email addresses will be shown at the end. So let's take a look at what we want to cover. This is the GitHub site. And again, there's all the code and all the documentation and the references to the data. What you will find on these GitHub pages is also additional information, how to get started, what's the context, what's the scenario, and then, of course, the description of the actual content of the actual exercises. I will start off and give you some variants and methods how you can load data, especially spatial data, into SAP HANA Cloud. I will, for example, use HANA or Python API to the predictive analysis library, so the machine learning capabilities. I will use that to load some data. The data is point of interest data, which we pull from OpenStreetMap. So things about bars and clinics and stuff like that. But most importantly, we will pull GTF data, which stands for General Transit Feed Specification. So it's a schema on how you could describe transportation schedules. So metro or buses or tram schedules. So the lines, when they are stopping, and where they are going. So this GTFS model, we'll take a look at it a little bit in order to then motivate exercise number 2, where we're looking at some graph capabilities in SAP HANA Cloud in order to do some routing on a spatiotemporal graph in terms of that we are looking for routes that we can take using public transport. And these public transportations, of course, are bound to certain schedules. So this is why this is a spatiotemporal problem. In exercise number 3, we are showing a couple of ways on how to import and export spatial data. So I will walk you through, of course, the shapefile import, but also explain a little bit what you can do with raster data, especially so essentially images, and how you could convert them and load them into SAP HANA using GDAL. I will also then have a couple of minutes on how to import and export graphs, so networks, and how, for example, to leverage Cytoscape for that purpose. Exercise number 5 is then demonstrated by my colleague Christoph Morgen, who will first of all apply a time series forecasting model on multimodel data. So he will show you nice data set related to gas stations and gas prices. And I will show you how to forecast fuel prices at gas stations. And in the last exercise, Christoph will build a machine learning classification model on multimodal data in order to classify these gas stations and provide some more insights. Let's take a quick look at the getting started section. So again, here I've described a little bit about the scenarios, again, mainly about that GTFS data set, the transportation data set, and the fuel prices, a little bit of documentation and links and how you could set up your own HANA Cloud trial instance, for example. Then some background information on certain applications or tools that we will be using throughout this workshop, which is mainly dbeaver, an open source database administration tool, which we will use to run SQL code and interact with the database. We will also use QGIS heavily, which is an open source GIS client. GIS stands for Geographic Information System. So this is the tool where we plot the data that we store in HANA and process in HANA on a map, for example. GDAL, for example, a reference here is a very, very famous software library, which I sometimes call the Rosetta Stone when it comes to spatial data. It is used in many, many software packages in order to transform different spatial data formats. And then HANA-ML, of course, is our Python API to the HANA machine learning capabilities, and HANA-ML to be used in the Jupyter Notebook in order to do some data science stuff. Last but not least, Cytoscape. It's a rich client to lay out and analyze networks, so graphs in essence. And since there is an adapter plugin in order to interact with HANA from Cytoscape, I will show you how to import and export networks using that tool. We'll also find reference to background material here, links to our online community where you find additional information. Let's get into the first exercise. What I will be showing you is a little bit how you can use HANA-ML in order to load JSON data and spatial data, especially point of interest data, which is a common task in many scenarios where we want to understand, okay, which are point of interest data in Germany or in a specific city. We will load point of interest data from Adelaide in Australia. And as already mentioned, we will also import some data from describing a public transportation network in Adelaide. So let's get started with that. A little data import task. This is a Jupyter Notebook running on Visual Studio Code. And this is containing first couple of code lines in order to import the data. What I already did is, for example, I imported the required libraries here. HANA-ML is one. So again, the Python API to machine learning, which also helps you importing the data. I've already used the connection context object of HANA-ML in order to establish a connection to my HANA system in the backend, because that's the target for my data replication. Now, as I mentioned, Getting point of interest data is quite common in some scenarios, in some use cases. We do it quite often. The way that I found is very easy to do that is by using the overparse API, so to say, that exposes data from OpenStreetMap. OpenStreetMap contains this point of interest data, and just to show you how it works, of course, there are many different ways how you can make that work, but this here uses the overparse API. I'm saying, okay, I want to collect cafes, restaurants, or bars at a 500-meter distance from the city center of Adelaide. So if I run that query against that overparse API, it will hopefully return some data, and we can look at the data. So this is a typical point of interest data set from OSM. So what we see is it's an espresso bar in Adelaide, and there are additional attributes assigned to this specific point of interest. So for example, which cuisine it offers. So this is a sample data point here. I will use HANA-ML again to push this JSON data set into a so-called collection, which is a storage element in SAP HANA Cloud, where I want these point of interest data to be stored to. So I just pushed it out, and we will take a look at that in a second. So as you've seen, the raw data from OSM is provided in JSON format. So if you want to flatten that data out in order to use its standard tables or flat data structure, you of course can also do that. So I'm using the very same data set, flattening it out, and then restricting myself to a couple of attributes. This is also one option how to transform the data, point of interest data a little bit in order to store it in SAP HANA. Again, I'm using HANA-ML here to create data frame from pandas element in order to populate a table with that data. So, okay, first task done. Let's take a look how that looks like. This is dbeaver, and I will show you and run a couple of SQL commands. And the first one is let's inspect the data that we just loaded into the HANA backend. So this is the JSON data stored in the HANA document store. So what you see is the first data point. It's JSON data you see here, and you can inspect it and interact with it. We also published the same data set into an SAP HANA table, so again, flattening it out and restricting it to a couple of common attributes like the amenity here, the cafes, and the names. Of course, these points of interest do have a geolocation, so a georeference. So what you see here is you can easily plot that data point on a map. So this is one of the benefits of dbeaver. Of course, once I have the data in HANA, I can do a little bit of analytics on it. Very simple. I can run a SQL aggregation statement in order to understand how many amenities, how many points of interest I got in my system right now. For later, we use a larger amount of point of interest data. So what I've just loaded, or just 100 or nearly 100 points of interest. For later, I will use a larger data set, and I will copy that data set from a prepared table. So if you want to run the exercises on your own, you can also skip the data import step and simply grab the table from where we provided it. So I created another table here called points of interest, and I will again just create some spatial data to it, which matches a suitable spatial reference system, which is suitable for displaying data in the Australia, in the Adelaide region. So there are a couple of different reference systems in which you can describe geolocations. We all know maybe the GPS reference system, the SRS with the ID 4326, which is a round earth reference system. What I'm using here is a projected reference system, which flattens the data. Okay, the next thing that we want to do, an additional step of data loading, we want to import the GTFS data, so the transportation schedules. These are provided online for various cities. I just took Adelaide. I've downloaded these data sets from that GTFS schema on my local desktop here. And I will use an import statement to create pandas data frames from these CSV tables. We will be taking a look at these data in just a second. The next step that I'm doing is from these pandas data sets, I will use the create data frame from pandas functionality of HANA ML in order to transport the data or write the data into HANA tables. So this is what this last step of my Jupyter notebook is. So while this is running, let's go back to SQL. What I want to quickly mention is there is quite a nice overview on GTF data sets, which are available out there. And I've imported that data. It gives you just a reference, a library of which cities, for example, offer these GTF data sets, and most importantly, offer real-time API to get vehicle positions, so bus positions or tram positions in real time, which we will show later. So this is just a library of certain cities which offer GTFS data publicly. And here, for example, you can see the Adelaide city offering the schedules, but also real-time vehicle positions and real-time alerts and that stuff. So I was grabbing the data from these public URLs. Okay, let's see which data we loaded. There is, first of all, in GTF as the concept of a route. The route is, it describes where certain buses are traveling from A to B. So for example, here you see there's a route ID number 100, which does have a name and it has a start and an end, so to say. So it's a general description of a route here. Then there are stops in GTFS. That's, of course, where buses stop in order to take passengers in or out. So, for example, you see here, every stop has an ID, it has a name, and it also has a geolocation, which you see down here. Actually, I just want to take a look at one. Here is a bus station or tram station or something like that. So these are the stops. Then, a very central concept of that GTFS dataset is that of a trip. So a trip is a specific bus running on a route, leaving at a certain point of time and visiting the individual stops along it goes. So a trip is an instance on a route, so to say. What we are seeing here is that there are trips running on certain routes, and we basically see that they are connected also to shapes. Shapes is what we'll take a look next. Shapes is the individual geolocations that actually make up a route. It describes the path that the bus follows, so to say. A little bit different than the stops. So the route is actually the path on the street, and the stops are individual stops where passengers can leave or hop onto a bus. So the last thing, while creating some data here, that I want to show you is the actual schedules. These are the stop times. So when do buses stop at certain stops? Let's take a look at that table. It's still replicating, it seems. Let me take a look. A little bit slower than normal. These are the stops. So essentially it says that the bus on this trip ID kind of arrives at this time and leaves at this time this certain stop ID. So these are the individual fine granular details of my public transportation schedule. Now, let's see again how stuff is made up. Here I'm using a function to basically, these are the shapes. It's still replicating the shapes, right? In stop times. Okay, let me switch to the offline mode while that replicates. What I wanted to show you is essentially these are essentially the stops that make up a route or a trip. So here are bus stations where you can hop on or hop off. The actual shapes that make up the trip's path are describing kind of this similar geometry, but of course describe the actual street path here. Now, what I wanted to show you is how you can concatenate a sequence of points into a line string. And that's what I wanted to do and show you how you can make that. You can use a pair of longitude, latitude coordinates and aggregate that together in order to form an actual line string and not just a sequence of points. Now, let me quickly check. Oops, still running. Now you may ask yourself why I'm showing you the details of the GTF data set. I'm a little bit convinced that if you're looking at this in detail and you are working with similar scenarios, like you are in supply chains or logistics or production, where you, for example, have a production line made up, and you're running production runs on that production line, maybe this data set and this schema might be very similar, and you can experiment with it and maybe learn from it. So, but still, what we want to do after this finishes is, let me see if I missed something. Okay, complaints about the stop times. What's wrong with my stop times? I'm not getting it. Did I delete something? Let's see. Okay, give me a second. It misses install and store on my stops, and I didn't generate that data, I guess. Okay, now we got it. I'm sorry for that. Okay. This was the part where I was creating line strings, so concatenating the individual sequence of points into a line string in order to visualize the actual routes in a better way. So for example, here you see a rather exotic route that, for example, a bus takes through Adelaide. I would like to associate these line strings, which describe my trips, to the actual trips, so I can query them in a condensed way. So again, we are seeing here the line strings. I'm doing the same thing with the routes, so to say, in order to analyze, for example, how many trips are running on the route. Now, this goes back to the core data model. Think about the route and the individual trips running on that route. And what we're seeing here, for example, the route ID botanic, which probably stands for botanic or something like that, there are actually 500 trips running on the route. So maybe starting very early in the morning, going to late night, and a very high frequency buses are traveling on that route. We will also generate a view that exposes the route as line strings, so we can take a look at the individual route, which should make a pretty similar thing as we've seen before. Now, let's take a look at how we can visualize that using QGIS. So I'll open a predefined workbook where we can take a look at this. So this pulls data from my HANA backend, so the actual tables and views that I just created in order to understand the transportation, and plots them on a map. So this is what QGIS does. First of all, we can take a look at our points of interest. So these are all the points of interest that are loaded earlier. So for example, you see that there are ATM machines, bench, bicycle parkings. Then there are the individual stops which are present in the transportation system of Adelaide. And we see the actual trip lines, or let's take a look at the routes essentially. So the routes actually cover the whole area of Adelaide and of course depicts that transportation network. Okay. Let's go ahead. One thing that we want to do with that GTFS data is that we want to pull for real-time vehicle position. So let's see where the Adelaide buses are currently underway. And I will also use a Jupyter notebook in order to do that. Again, I've loaded some required libraries in order to query the data for the real-time vehicle positions. I've connected to my HANA system, and this is how I'm doing it. So there is essentially a library from Google which allows me to read the specific format of that real-time vehicle positions, which is in protobuffer format. Here is the URL that I'm calling in order to get these vehicle positions. I'm just creating a Python function which calls that API and gives me a pandas data frame back. So this is the real-time vehicle positions of vehicles currently running in Adelaide, Australia. What we see here is that we have latitude and longitude, so a position. We also have the vehicle speed and stuff like that provided by that real-time API. The last thing that I want to do is I want to store these real-time vehicle positions. And I'm using create data frame from pandas as the core function here to get the vehicle positions and write them into a HANA table. Essentially, these are two HANA tables. One will keep the history, so over the course of a couple of minutes, and the other table is just storing the latest vehicle positions just retrieved by that API call. The way that I will run this store location function I just created, so I will run it every 15 seconds, so we get a real-time update of these vehicle positions. So I will start that, and in the background now my tables are created and are populated. This is my real-time location. I currently have 130 vehicles in that real-time table, and we can take a look at it. So what we see here, these vehicles have a certain ID, they are underway on a certain trip. And of course, as we've just seen in the pandas data frame, there is a latitude and longitude, essentially a geolocation attached to that vehicle position. In order to visualize these real-time vehicle positions, I will be creating two views which just reference the time delta, so to say, so I can do a nice plot of real-time vehicle positions. So let me open another QGIS workbook in order to see what's happening in Adelaide, Australia currently. So again, this QGIS workbook pulls data from my real-time location table in the HANA backend. And once that opens up, we see here are the individual buses and also the heading or the direction that they currently have. This is really real-time information. We can also see on which route these buses are traveling. So zoom in a little bit. Understand that this bus is running on this route here. You also see that bus down here. Let's take a look at the historic data that we collected in the last 1 or 2 minutes or so. Now you see that we actually have a kind of a trace of a certain vehicle. So that vehicle down here has been in the last 60, 80 seconds here running down that road in that direction. This is how you can bring in real-time data in to a QGIS workbook. You can even schedule a refresh of that map once the data is brought up to date every 15 minutes. Okay, Let me stop that running function in the background that fetches the data and quickly recap of what we've seen. So we have pulled real-time vehicle positions using a public API. That API provides data in form of a proto buffer format. You can use the create data frame from pandas in order to store that data in a HANA table and update that and pull from that HANA table into a kind of an online map in order to understand real-time vehicle positions along with their, in this case, 5 minutes traces. The last thing that I want to show you is how we can use a specific function, the distance function, in order to understand if the real-time vehicle position somehow makes sense, if the vehicles are actually on the trip they are supposed to be. So that's why we are comparing our real-time locations to our geometries that we derive for the actual trips. And we are calculating the distance between the real-time vehicle positions and the actual trip lines. So the first thing that we see is that there is data errors. So 0.00 is for sure a data error. Here is a vehicle at a certain point in Adelaide, which is pretty far away from its trip where it's supposed to be. So you see the vehicle is up here currently, but the trip on which it's supposed to be is the brown line down there. So it's currently 9 kilometers away. Of course, that's not normal. Most of the vehicles are actually currently on a position which is on the trip where they are supposed to be. So here, pretty close to where it needs to be. Okay, this concludes exercise 1. So what we've seen is how we're using HANA-ML in order to load some data, especially some spatial data, and how we can use certain functions in HANA to create, for example, line strings out of a point or a sequence of points, and how we can connect HANA to QGIS in order to plot data from HANA on a map. Now, one of the reasons why I loaded that transportation data, that network data, is also to show you some basic examples on what you can do in HANA when it comes to network processing. So what we will do is we will take our GTF data and construct a network out of it and create a so-called graph workspace. The graph workspace is that object in SAP HANA Cloud which tells the graph engine on where the data is and how it is organized. So this is the graph model, so to say, that we expose. And after that, we will running certain procedures and functions provided by the HANA graph engine in order to find some paths. So let's do that. A graph is made out of vertices and edges, or nodes and relations. And the first thing that I will do is I will create the edges of my graph. So what are the edges? The edges is whenever a bus can take you from one stop to another. So this connection from one stop to another will become our edges in our graph on which we want to do routing later on. So I will create an edges data structure, basically connecting each stop of an individual trip together. So in my case, I will just replicate the data or create a little bit of new data. I will add an identifier to it. I will kind of do a proper formatting for the time formats and calculate, for example, distances and travel times here. So let me execute a couple of lines of SQL and take a look on what we just created. We created the edges, so the edges that make up our network, our transportation network. So what's in there? Our data has a source and a target, which right now matches the stops on which the individual transportation vehicles can take you in or leave you out. Of course, there is a departure time and an arrival time. So this edge starts here, ends there, and it takes from 3:35 to 3:36 and a little bit, and which makes up for a total time difference of 56 seconds. Or 111 seconds. So this is what we will use later in order to find the fastest route on our transportation network. So we've just created the edges. Now, of course, you can hop from one vehicle to another if they share the very same stop. So you can leave that bus and go on a tram or something like that. But of course, you can also walk. So in our simplified model, we're adding edges between stops where you can walk. You can walk at any time, as opposed to buses which leave at a certain point in time. So what I'm just doing is I create some edges in my network, in my edges table, that represent edges which you can walk, where you're free when to start. And finally, because we want to find a route from a certain start point to a point of interest, for example, to a pub or to a clinic later on, I'm also connecting my points of interest data set to my stops here, so that I can walk to the point of interest. Okay, let's see what we just generated. We generated edges in the network, which are now not transportation edges, but which are walk edges. So I can walk from here to here. So the transport type is walk, and it will take me 29 seconds, which is calculated from the actual spatial difference between the source and the target. So what would we have now in our edges table, in our network table, so to say? So there are roughly 800,000 edges, which are of type transport, so where buses can take you. And there are 200,000 walk edges. So where I said, okay, this is with a tolerable distance where you may want to walk over. The last thing that we are doing is we're creating the vertices, the nodes of our network. So we basically take the stops and the points of interest into our vertices table. Now, taking a quick look at the vertices, these are just, for example, stops here in this case, which we got from the transportation network, but there is also points of interest data like police stations, which we want to route to in our network. The last thing that we need to do is to create a so-called graph workspace, which tells the graph engine on where the network data is, just pointing to my edges table and to my vertices data structure. This is all I need to expose the data to the graph engine. Now, nice one. What can we do with the graph engine on this spatio-temporal transportation network? The first thing that we can do is can find a shortest path. For that, we're creating a database procedure. So a piece of logic that runs in the database near to where the data is. So I'm creating that function actually. It takes a couple of input parameters. So start location and an end location. So again, I want to find the fastest route between the start and an end location. And it provides an input parameter where I can specify when do I want to travel. Of course, I need to find the right schedule, the right combination of public transportation at a certain point of time. That may be different if you want to travel at 3 o'clock in the night as compared to 12 o'clock in the afternoon. So that function is written in a language called Graph. It's a domain-specific language which provides, for example, built-in algorithms to calculate shortest path. And this is what I'm doing right now. So within these couple of lines of codes, I refer to my graph workspace, which I just created. I create a start and an end vertex based on my input parameters, and I will call the shortest path function. Now, this is here where where a little bit of magic is, because I need to check for every edge, is it a valid edge? So think about a bus that left 5 minutes ago. I can take that bus. So this bus this edge is not a valid edge for me traveling. So I need to make sure that the edge I'm taking, the edge I'm exploring, the edge this shortest path function finds for me is a valid one that is in the future, that is done here. However, I can always take a walk edge. So that is not restricted by time, of course, but it just takes me a couple of seconds to go from A to B. There's a little bit of magic on how to calculate, how to expose the time it takes to a certain edge, to take a certain edge to that shortest path function. Let me generate that function, so it's available in HANA Cloud, and call it essentially. Here is how we're calling that table function. We want to go from this start vertex, which is somewhere in Adelaide, to this end vertex, which is a point of interest somewhere at 8 o'clock in the afternoon. And this is the core of the SQL query that I'm just running. It's a call to that shortest path function which I just created. And this is the result. The result is essentially a set of edges which I need to take. Describe, walk a little bit. Thanks for that message. Hope you can still hear me. And then I can take a transportation, a certain trip, which takes me down the route. Let's see, there's of course also in plot the path. So I started over here, I had to walk down there, then a bus takes me to here, then another bus takes me to here, and so on. So this is all what is included in the result of my shortest path function, which I created. So which stops I'm visiting, where I need to get out in order to walk, and stuff like that. Now, finding the shortest path is one thing. There is also the possibility to not only find the shortest path between A and B, but essentially to find the shortest path between one start point and all end vertices in the graph. Essentially, what is used in this table function here now is the built-in shortest path one to all function. My function just takes a start vertex and calculates the distances, the travel time I need to any other location in my network, taking into consideration the actual schedule of my buses. Let me show you quickly how the result that works here, because we're just creating a few around that in order to visualize the data in QGIS to make better sense out of it. So let me open up another workbook, which pulls up these isochrones. So again, I'm starting from a certain location and calculating for a specific point in time how much time I need to get to any other location that is reachable in the Adelaide city. So this is what this view exposes. I have been starting at a location down here, that green dot, and this isochrone plot indicates how much time I need to travel by public transport to other areas in the city, where red indicates a long travel time to get there, and the lighter colors, of course, which are closer to my start point, indicate lower travel times. The last thing that I want to show you on this transportation network is how you can query the graph to get the top K nearest reachable vertices. So what I want to do here is at my start point, I want to understand which are the 5 nearest pubs which I can reach by public transport from my start location. This kind of query, this kind of analysis is very common also in other use cases. So for example, in utilities, if you think about an electricity network and you have a connection, house connection, you would like to trace that network and find the nearest transformer station or the nearest 2 kind of assets of a certain type. Again, we are creating a database artifact in HANA using the graph language, but now we are using the diverse Dijkstra operator. It lets you start at a point, it traverses the network in the shortest path manner, using the very same cost function that we had before, either walking or taking transport. But now I'm hooking into each visit of a vertex. So whenever I traverse over a vertex, I inspect that vertex and say, hey, are you a point of interest? Are you what I'm looking for? Are you a pub, for example? And if so, we collect that as a piece of that result of that function. So it may look wild, but these are just a couple of lines of code which we can generate once in the database and then use to query. So what I want to do, starting from my start location, I would like to, at 8 o'clock in the afternoon, I would like to reach a pub and I would like to return the top 5 nearest or fastest reachable pub. Let's call that function and see what the results look like. Now, here are my 5 pubs. I was starting at this location. Here are 5 points of interest of type pub. And if I'm looking at their geolocations, I find that I was starting over there, and these are the 5 pubs which are fastest reachable by using public transport. Now, of course, I can also say, okay, I'm not interested in pubs, but I'm interested in clinics and run the very same thing. And I guess the point of interest is named clinic. Now I find 5 clinics which are close to where I start and which I can reach by public transport. The function also returns the actual paths being traveled for each start location up here. I can inspect the individual paths which I need to take in order to reach these clinics. So that was it for the second exercise. We will switch the content a little bit, so bear with me. But just to recap, we were looking at routing on a spatial temporal graph. We were taking the GTFS dataset, so the public transportation dataset, and we're creating a graph workspace from that. What we would need is edges. There are transportation edges where a bus takes you from one stop to another. There are, of course, also walking edges where we can change the vehicles and by walking over to another stop. After we created that data set, we created a graph workspace. It's a kind of a view that tells the HANA Graph Engine where data is located. And then we were exploring shortest path and especially the traverse Dijkstra operator as part of the built-in HANA language for graph analysis. We were using the built-in shortest path function to get from A to B. We were using the built-in shortest path one-to-all function in order to generate these isochrones, so kind of reachability analysis for a certain start point to other areas that are covered by my transportation network. And finally, we were using the traverse Dijkstra operator to start from a location and understand the top K points of interest that we can reach in our network. Okay, moving on and switching the context a little bit, importing and exporting spatial vector and raster data. So far we've been using the point of interest data set and GTFS data set, which mainly was a point vector data set, so describing georeferenced locations. The next thing that we want to do is import some other data sets in our HANA database system. And for that, for the first part, I would import spatial vector data, which describes geometries. And in the second part, I will import raster data, convert and import raster data. Again, these are kind of image files. For the first piece, this is Database Explorer that I'm using. I'm connected to my SAP HANA system in the backend, and now what I want to do is import data. In this first example, I will import S3 shapefiles, which is a very common data format for storing spatial data. I will browse to my shapefile, which describes land use data. So again, in the Adelaide version, Adelaide region, which areas of the city are used for which purpose. So where do people live? Where is agriculture? Where is commercials and things like that. So I import that shapefile into my database schema. I give it a spatial reference system, which the data is defined in, and I'll hit import. So now that shapefile is imported into my HANA table. It says success. Let's inspect what we just imported. This is the table that we just populated. There are 12,000 geometries being imported, and these geometries are small areas in the city of Adelaide, which are, for example, in this case, are categorized as agriculture, maybe because there is trees there. And of course, I can do some analysis in HANA with that data, but what I want to show you again is in a QGIS workbook, how this data looks like. So import export spatial, this I was looking for. So the table that I've just created contains data describing the land use of Adelaide. And here on the right-hand side, you see the color coding. So there is a lot of residential areas. The blue ones are recreation or reserved. So this is the data set that I just uploaded. One nice capability to actually upload data in other file formats other than SVA shapefiles is via QGIS. So as the integration is bidirectional. For example, a less common file format for spatial data is KML. So I can just pull this KML file into my QGIS canvas. And this file describes kind of administrative boundaries, wards in the Adelaide region. And from here, from QGIS, I can very easily just upload the data by dragging, dropping it to my HANA database system, which is referenced up here. So now the upload to HANA already started, and it should be finished in just a second. So I've pulled the KMA file just onto QGIS, and from QGIS, I pulled it into my HANA backend system. The import was successful. Let's quickly inspect the data. These are the wards. These are the ward data that I just created. And you can see these are polygons or multi-polygons describing these administrative boundaries. Now, what you can also do instead of import, for example, you can also export the data from here. So you can just right-click, for example, on my isochrone dataset and simply say export layer. And then you can choose a certain file type, for example, SV shapefile, and export the data from HANA into a specific file format. All right, this would be the other way around. Now, what I want to show you as the last piece of that exercise is how to deal with raster data. So raster data is basically images where certain spatial characteristics or meshes are contained. So this raster file, this image file, and you actually see the individual pixels down here, this describes the estimated population. It's taken from a larger data set, which describes world population in resolution of, I guess it was 100 meter by 100 meters. So what you see here is the lighter the pixels, the higher population density in that area actually is. Now, this is an image file. In order to store the data in a database and analyze the data in the database, I need to convert that. And there are two most important options in how you can convert an image file, a raster file, to a vector format, so to a geometry. And one of that option is by calculating contour lines, like you know from hiking maps, where you have contour lines describing the elevation if you're in the mountains. This is one thing that we will be doing. The other thing that we'll be doing is we will be polygonizing. Polygonizing means adjacent areas where the measure, in my case, the population density, is identical, will be aggregated into a polygon. So in both cases, we are converting pixels into geometries. When doing contouring, we are generating polygons describing these contour lines. When using polygonize, we are aggregating similar pixels with the same measure into a polygon. Now, the software library that does that in most of the software packages and also in QGIS is called GDAL. So GDAL is an open source library, which you can very quickly also get with QGIS. So it's a part of the QGIS distribution, so to say. And what I want to show you is actually how we can use GDAL, so that bare bones software library, in order to convert our data, our raster file. The first thing I'll be doing is I will run GDAL contour. And this is, for example, an interval on which contour lines will be generated. I hit enter. Now GDAL is taking the data on my desktop and converting that raster file into a shapefile, converting that raster file into a vector file. We'll be taking a look at this in a second. In a very similar way, you can use GDAL to polygonize. So let me also quickly run this one and take a look at how that looks like. Let's do one other thing first. Populating polygonized version also into a HANA table. So the raw contour file, which I just created, basically looks like that. So as you can see, if you're zooming in, these are contour lines describing not the height, not the elevation, but the population density in that area. And if I switch over to, hopefully that upload had already finished, and show you how the contours look at the end. Opening up a QGIS workbook, which again shows you how these contour files look like. So this was the raster data format that I had before. What I created is these contour files. So these describing areas where the population density is above a certain level. And that level was depicted by the interval that I've chosen. So we see population density from 0 to 10 up to 170 persons per, I don't know, 100 square meters or something like that. So this is giving you one insight how you can use GDAL and its HANA connectivity in order to convert raster data programmatically into vector data, load that vector data into a HANA file, into a HANA database. Now, the last thing that I want to show you quickly is a couple of things related to spatial clustering, how you can aggregate, how you can condense spatial data. And the first thing is a very easy option here, where remember our WAR data, so the administrative boundaries, we can simply count the number of points, the points of interest, by doing a join between these two tables using the ST within predicate. So we're counting the number of points of interest which are within a specific ward, which is sometimes called fixed location clustering, where we see, for example, the central ward contains nearly 2,000 points of interest. The other option that you can do is you can not cluster by these fixed geometries, these wards, but you can cluster by using a generated hexagonal or a rectangular grid, for example. This is built-in function in SAP HANA, and you can invoke it by using that group cluster by syntax in SQL. Let's see how that looks like. This function generated a set of hexagons tessellating the plane on which my data resides, and giving you certain aggregation possibilities. Here again, I'm just pointing the number of points of interest per hexagon cell. So for example, in this hexagon cell, I have 166 points of interest that are within that area. The last spatial clustering method I would like to show you is one that is not restricted to point geometries. So remember, we've just clustered points of interest, one time by fixed location, fixed geometry, these wards, one time by a generated geometries, which were the hexagons. What about if we want to cluster more complex geometries, like the lines, for example, our route lines from the GTF transportation network? And for this purposes, you can use the so-called grid generators. Grid generators are built into HANA, and what they give you is simply a plain grid defined by certain boundaries. They just tessellate the plane. Now, what we want to do is we want to count the number of trip lines that go through these hexagon grid cells. And for that, I'm using again a join, and I'm saying whenever that trip line intersects with that hexagon that I generated, I count it. And so by that, I can aggregate non-point geometries. That means my line shapes here. And creating a view in order to give you the visualization again in QGIS. This is how the result looks like. So these are hexagons where the color indicates the number of trips from my public transportation networks runs through that hexagon grid. And if we compare that to our route lines, which we generated earlier, you of course can imagine that there are many more buses, many more trips going to that red area. And if we go further down or further away from the city center of Adelaide, we will have less buses or trams going through that area. So that makes up this plot for where we aggregated the trips along hexagons. So this basically concludes the third exercise. What we've seen is we loaded spatial vector data. First of all, these land use data using from S3 shapefiles using the Database Explorer. This ended up in a visualization in QGIS, where we have color-coded the individual land use in downtown Adelaide. Then we've used QGIS to import a KML file describing administrative boundaries into SAP HANA using drag and drop. And last but not least, we have converted raster data describing population density using GDAL and uploading data generated from that raster data, also using GDAL directly into HANA. And from that, we've generated these contour visualizations, as well as what you've not seen is these polygonized representations of world population, where of course, similar color indicates similar population density. So last thing, we have looked a little bit at spatial clustering, fixed location clustering, hexagon clustering, and hexagon clustering of 9-point geometries. So resulting essentially in that visualization down here for calculating or aggregating the number of GTFS trips by a generated set of hexagons. Now this concludes my third exercise. Very quickly on the fourth exercise before I hand over to Christoph for the machine learning part. Let me quickly describe that. What's going on in here. So basically, I'm creating another network. So I'm looking at my public transportation network, and what I want to understand is how individual routes are related to each other. And the relationship is determined by the number of stops they share. So I'm creating a kind of a meta network on my transportation network where I say, okay, two routes are strongly connected to each other if they share a lot of stops. They may be not connected at all if they don't share any stops, if I can't get from one route to another. This is what I will be doing in SQL. And let me quickly run that. So I'm just creating, for the sake of time, I'm creating some edges. Again, understanding or I'm creating some edges data. And this will be used in a graph workspace. And what you recognize is I'm not creating a table, but I'm using a view to expose the data to my graph engine. So what we do see is creating a network where a route or route group, to be specific, is connected to another one if they share some stops. For the vertices, I'm also just creating a view that exposes these individual route groups. I'm creating a graph workspace that exposes the data to SAP HANA. Now, one thing that I would like to show you is how you can use Cytoscape in order to import the data and do some analysis in that Cytoscape rich client. And for that, I'm using a plugin for SAP HANA where I can connect to my database. And I can use the very same plugin to load a graph workspace. So this is the graph workspace that I just created. Now it grabs the data from the database. And once that succeeds, I can create a layout of the data. Okay, let's cut that short due to bandwidth problems, I hope. So what I wanted to show you is how to use QGIS, so that third-party network analysis tool, in order to visualize data coming from SAP HANA. So this is my transportation network and how individual routes are connected to each other. And so we can try to understand the topology of how things are made up in the LA transportation network. The second step then would actually be how to get a data that resides in Cytoscape and pull that into SAP HANA. This is also possible by using that plugin where you can, for example, use a standard network data format, for example, GraphML, where you import a data set into Cytoscape and then use the HANA plugin for Cytoscape in order to push that network from Cytoscape into the HANA database in order to do some advanced processing there. So that basically concludes the fourth exercise of that workshop. And I'm now handing over to Christoph Morgen in order to cover the machine learning part of the HANA multimodal capabilities. So I'm stop sharing. Christoph, you can take over.
Thank you very much, Markus. Can you hear me?
Yes, that's fine.
All right, and I guess you can see my screen as well. Okay, then let's continue with exercise 5 and exercise 6. As Markus already explained, in those two exercises, we will be looking at the machine learning part of the HANA multi-model or smart multi-model capabilities. In exercise 5, we are actually looking at the forecasting time series analysis part on multi-model data. So we want to use the Python machine learning client, which we've seen Markus been using. And if you also watch the TechEd keynote, there was also Vitaly using this Python machine learning client, using Jupyter Hub, the application I'm using here, to basically script in Python, but generate SQL on the fly and push down all the processing into the HANA database. So we will do some preparation of data using the data frame, which you've also seen Markus been using. You'll see some more methods coming to the game of kind of scripting in Python and using the HANA machine learning client, and then apply some forecasting techniques on the data. The data scenario we're actually using is about fuel station data in Germany, where we will upload location data and the actual fuel prices of each of the 15,000 or over 15,000 fuel stations in Germany, and you will be surprised how often there are price changes for every fuel every day on every station. Okay, then let's get started with the exercise. Like Markus did, first and foremost, we are loading the Python packages here. The HANA ML package is the machine learning client. The actual database client for Python is HTTP CLI. That's loaded implicitly if we work with HANA ML. We're using the latest version, 2.14. I think similar version Markus has been using. Now we're connecting to the database. Markus used the client connection key. I'm actually specifying here user, password, host address, etc. explicitly, and connecting to the same HANA Cloud system using a different user in this case. Next is we want to prepare and download the file. So that's what you would be doing. If you download or clone the repository to your local project directory for exercise 5 and 6, we have the subdirectory fuel price, where there's some data prepared, others you need to download. Here are the links to the actual pages. For example, the fuel price data you would be downloading from this web page here called Tankerkönig, where you can actually download the fuel price data for every day for a couple of years if you want. In this exercise, if you clone the project directory and downloaded some of the fuel price data, you would have your data directory like this. You see there's some shape files, which we have seen Markus also uploading to the HANA database. We have some fuel station CSV files, and we will now continue and start uploading them to the HANA database. And we will load it to our user's local schema. In my case, it's TechEd user 999. Like Markus did, we will use the function create data frame from pandas. So the first thing is we load the CSV file into pandas data frame, and then the pandas data frame will be converted into the so-called HANA data frame, which is that virtual placeholder over data stored in SAP HANA. So we create a table called gas stations. We will override if the table already exists. And a nice feature is we actually can directly create geolocation columns of type spatial as we load the data and we create the HANA data frame on the file. So let's do that. And as you can see, the data is uploaded, and I'm using the head and collect method, so I can basically inspect what's now behind this data frame stations _HDF or HANA data frame. we'll see as UID, the station ID, and some information about the actual fuel stations, including the last column, which is my spatial column type, spatial point stored here, which is the point location of the actual fuel station. As next, we want to import a shapefile, similarly using the Python machine learning client. Markus showed the same using the respective QGIS interface and the database explorer doing so. And here we are using a method from the Python machine learning client called create data frame from shapefile. So we directly referring to the shapefile, in this case it's a zip of the different spatial formats that is automatically picked, and we're creating a HANA database table, geo Germany regions, and we can certainly then also inspect the data being loaded using the collect methods. The collect method is actually the only point in time when we transfer data from the HANA database to the Python runtime here. And as we are specifying head 1, we're actually only collecting the very first row. So it's basically a top 1 clause against what is behind this data frame regions HDF. And we will see later on more examples like that. Okay, now we want to use some spatial methods along with the data frames to filter down the stations which are close to the SAP headquarters, near Heidelberg, Mannheim, and the so-called Rhine-Neckar-Kreis. So we have the two data frames, the regions data frame and the stations data frame. We now use the filter method, which is basically a where clause against the regions data frame, as we want to filter down to 3 of the regions which are in this file, and then use a spatial join method here, the intersect method, to basically filter to the stations which are part of any of the 3 regions we have been filtering on. So basically instructing a spatial join from the Python side. And if we use the select statement attribute here behind the data frame, we actually always see what is the SQL being generated on the Python side and executed against HANA, if we then specify the collect method, for example. And as we can see here, there is the respective spatial join methods applied as part of the SQL statement. And we have 171 stations in the respective area. If we now want to visualize the stations in a map, we want to visualize all the stations. So basically we're doing the reverse join. What are the stations except these 171? So we basically executing the same query, just negating the filter, and there we're getting back 15,263 stations. And if we now want to visualize those stations, what we basically will be doing here, basically pulling back the information about the station points from the HANA data frame into a pandas data frame, and then from the pandas data frame creating a so-called GeoPandas data frame, as we want to use some tools in Python to visualize this GeoPandas data frame. So we're actually doing something which we typically don't want to do, collect the data and then visualize it in Python. And that I've also already prepared here is that we see a map of Germany, as we have all the boundaries here displayed of the regions, and then the blue spots are all the fuel stations all over the country, and the red ones are the ones close to the SAP headquarter region. So As next step, we want to upload the CSV files for the actual fuel price information. And as we have downloaded all the data into directories here, for example, the month November is in the subdirectory 11, and you could use different kind of approaches to doing so. I'm iterating over all the files here in this directory, and using again create data frame from pandas, but using the append method to just append what has been loaded by the current file. This is just an example. I've actually pre-done this for all the days throughout this year until Sunday, so until the 13th of November, which gives me basically a very big data set of size over 106 million records or price changes over all these 15,000 fuel stations in Germany in this data set. And if we now analyze that using some methods, again, the data frame here, the aggregate method, basically count how many fuel price changes do we have per station. We have 15,000 stations, 106 million price change information in the data set. Basically means that for every station we have about 7,000 price changes on average, meaning 22 price changes every day on average for each fuel station, which is actually a lot. So if we now want to visualize that price data, then we can execute some histograms here as part of the HANA ML package. We have some exploratory data analysis visualizations like the distribution plot, and we can see here, okay, there must be some outliers in the data. Therefore, let's run this again, but filter down the data for the E5 fuel price, which is basically the type of fuel which we are focusing on, and look at the price band between €1.30 to €2.80, and as kind of a value range which likely makes sense for that time period. So that's looking better now. We don't see a large number of outliers in price areas which wouldn't make sense. We can also visualize the complete 106 million data sets in a visualization. We have a method called M4 sampling, which is some smart time series sampling method, which kind of samples the data to the size of the visualization we are creating. And at 210 is basically a pixel related indicator to the visualization we are want to see. And based on that, we will get an overview on the complete data. And it will show up in a second. And and here we can see the overall fuel price data. We see some changes here end of March, where we ran into this global war crisis, and some other changes here end of June and end of August, beginning of September, due to some price regulations in Germany specifically. But there's also another nice visualization, the time series box plot, and there are more if you explore the HANA machine learning client, which basically aggregates the data using these box and whisker charts for each of the calendar weeks or months if you want. Also a little bit better indicating how the price, average price and price, let's say, distribution behaved over time. But now let's look into the actual forecasting. So what we want to do for each of the fuel stations close to the SAP headquarters, those 171 fuel stations, model forecast model for the actual fuel price E5. And basically all we can do is look at what regular patterns can we deduct from the forecast data. Certainly we cannot forecast these dramatic changes imposed by the global crisis we have seen. So basically the forecast model will focus on what would be daily patterns, what would be regular weekly patterns, what would be regular monthly patterns, or other change points, basically maybe derived from typical holiday vacations and other external regular events. So that's what we want to do. The data, again, we will be looking at. We are filtering the data based on the stations. So we are selecting the stations which are within those 3 regions near the SAP headquarters. And basically doing so, we again see it's the 171 stations, and in a second we will see an excerpt of the actual fuel price data. And just give it a second. And okay, again, we are aggregating and collecting from 106 million data points. And as we can see here, then we have the date and we have the station IDs and the actual price record. And as we have filtered down for the 170 stations, we only have now 1 million, a little bit above 1 million rows as input to our forecasting tasks for the 171 stations. Now let's identify the actual starting point and end point of the time series data. It's November 13th, this Sunday. And as we want to kind of challenge ourselves and determine the quality of the forecast, we are basically using a time filter to filter for, let's say, the last week of data, which we want to use for testing the time series. So we model with all the data until November 6th, and with the data between November 6th and November 13th, we will then test the forecast result. So that leaves us with 30,000 rows for testing our forecast results, again, for the 171 stations. We could now also add holiday information, so external time information about special days, indicating potential regular change points in the time series. We're basically passing in an empty table, and we now want to use the profit implementation of that famous forecasting algorithm in the predictive analysis library called additive model analysis. And also to speed up, I'm filtering down from 6 down to 6 stations instead of running the forecast for the 171 stations. So using this PAL algorithm and running it in parallel over this 6 stations here, and letting the algorithm know, please identify daily seasonalities, weekly seasonality patterns, identify change points, and running these in parallel, specifying again this massive parameter and specifying the station ID. And with that, we actually have calculated these 6 forecast models in parallel. We ran this for the full 171 gas stations. It would take about 190 seconds. What actually happened behind the scenes, like we saw in the keynote, we can generate the actual SQL code, basically also directly generate this into design time artifacts. Here I'm just revisiting what has been executed, and I'm seeing that the PAL procedure, PAL massive additive model analysis, has been called. And we also see the filtering of the input data passed into the data frame. How do now the segmented models for this profit additive model analysis look like? There's the model data frame results from the additive model analysis object I have created, and we can see there's, for each of the station, there's an individual model. And if I would now want to forecast using that models, I can use my test data frame, which I've created before. We have created before, use the predict method, and using that predict method again in parallel for each station ID using the individual models, then I would get decomposed information if that's of interest for me for each group ID, and giving the date, the forecasted value, the lower and the upper bound forecast, let's say confidence interval, and the decomposed information about what's the trend proportion, what's the seasonal proportion, etc., of the respective point in time and forecasting values. If there would be errors in the data, that would be given to us by the error result data frame. I can now also visualize the forecast for an individual station where I'm actually uniting the actual, so the data until the 6th November with the data from 6th to 13th November into one data frame, and then adding the forecasted values. And then I would see that's the actual data and the forecasted values, and then I could simply plot the respective forecasting visualizations here. Using the forecast line plot method, again, from the HANA ML client, and the visualizations pushing down all the, let's say, aggregated processing into the HANA library and just passing back the results. Just take a second, and basically what we see in this first plot, the complete time span again, which again highlights what happened over the year with respect to irregular changes due to the crisis with the forecast price data, and the price drops here in mid of June or end of June and end of August. The rise again due to the local regulation in Germany and the respective price changes there. If we then run this again for the time period from October 23rd to 13th of November, we get a nicer forecast plot and idea about how the forecast model behaves. And we actually see that the forecast model very nicely managed to identify the daily pattern of the price change. And that's something maybe many of us would not have expected, that there's such a regular daily pattern for the fuel prices. In the optional exercise, which I not demo due to the time constraint, is which indicates you how to evaluate the forecast accuracy here. Again, bringing together the actual and the predicted data for the period from the 6th to the 13th of November, and basically then running the forecast accuracy measures here, which will give you then all the detailed statistics about the forecasting quality. Now in exercise 6, on the same basically scenario, what we'd like to do is classify our 15,000 stations, and we want to classify the stations based on, let's say, their price class. We're building a category of the average price levels for the E5 fuel. And we then want to use machine learning techniques, hybrid gradient boosting model to see which of the informations, the stations attribute we have at hand can describe best this difference in the price class. And we will specifically use some of the spatial derived features to see if they influence or have influence to the price categories here. So I'm loading the packages again. I'm reconnecting here with this notebook to the HANA database, same as I've done before. So that's nothing new. And as the first step now, I'd like to create, I don't have a classification yet, so I'm artificially creating a station class column as our model target column. For that, I'm actually picking up the E5, and there's another measure, the E5 change. So the number of changes basically per day, or if a figure included a change or not for the E5 fuel. And then I'm averaging that over day and then over the station in general. So I basically have an E5 average value for each station, and then I'm using the binning HANA SQL function to create the class of the station class, and depending then of the level of the average E5 price will basically then determine the station class. And I'm using again the connect message to HANA and the basically free form of a SQL statement using those brackets here to be able to specify a long and multi-line statement SQL call. So that's really nice if you have a complex SQL statement which you'd like to issue from the Python side. So as I'm executing that, as you can see on that 106 million really fast aggregated information about these 15,000 station IDs. Now I'm creating some, let's say, attribute data frames. The first one is my master data. If you want stations data frame, stations HDF, and I'm just subselecting a number of columns here, the ID, the brand, and then from the postal code, I'm actually just using the first two or the first 3 digits here to have a more, let's say, abstracted kind of information, which certainly also have some location information. The same here for the city. So that's my first dimension, basically, to the problem or feature I'd like to identify. Next, I'm creating a price level indicator data frame. Basically, I'm again starting with the E5 values and E5 change indicator, calculating day and an hour, and I'm then basically counting how many E5 changes did I have per day, or what is the minimum E5 value per day, or what is the range of E5 value per day. And then I'm again, as I have the value for each station, for each day, I'm averaging this again. So what is the sum of all E5 changes over the complete time period? Or what is the maximum value of changes per day? Or what is the average minimum E5 price value? What is the average range of E5 values for a station? Just trying to come up with some, let's say, numerical price indicators, and creating this data frame again. And what we will see, some of them are highly intercorrelated in order to kind of not to put too many intercorrelated values into our actual model finding, into our machine learning classification algorithm run. We're using the correlation plot here to visually explore, and again, everything, the correlation calculation is pushed down into the HANA engine using some of the PAL functions to identify the intercorrelation between the different, let's say, artificial numerical features we created before. And as we can see here by the color, that some are highly correlated, the minimum number of E5 changes and the sum, if we want, of E5 changes are highly correlated. Correlation factor here of 0.79, so maybe we shouldn't use that. And in order to, as I said, kind of only put in a smaller number of non-correlated values, we basically only use those which are have a correlation of lower than correlation coefficients of lower than 0.5 maximum to the basically our target numerical information. We use the average E5 price. That leaves us with here 5 numerical indicators. So now we're coming to the spatial attributes. What we can use is a function called geohash. A geohash is a unique value of 20 characters, a hash string, which identifies a point location. And we can now substring, for example, the first 5 characters of these geohash values, and any other substring having more than 5 characters from the first, from the leading one counted, will then be a point or an area within that 5-digit or 5-character geohash reference. And therefore, what we can do, create the so-called spatial hierarchy using a feature generation function here by using the geohash hierarchy and specifying, we want to create 3 geohash columns. And what these look like, we will see here in a second. So basically what we have done from this point location, we created this 20-character geohash, but we only kind of left the 3-character, 4-character, and 5-character geohash, which is basically a hierarchy, which we can see from the geohash values. But a really nice spatial derived information is that we calculated the distance from each stations to the highway network. And this one we have prepared. It's actually described in the add-on section of the exercise, where we have imported from the OpenStreetMap network the highway, if you want, vertices and edges, and created a multi-line string object in the HANA database, and then use the spatial functions to calculate the distance between each station point location and this one big open highway network if you want multi-line string object. But this we have prepared here as a CSV file, which you can then import again. And again, we're using create data frame from pandas, specifying the table structure, which we want to import this to. And then we're basically using a join between the imported station's highway distance and our spatial hierarchy data frame, which we created before, which then concludes or has all the spatial information for each station ID. Longitude, latitude, the point location, the geohashes, and the highway distance. And finally, we can again join the data frame we currently have with the regions data frame and adding some more columns like the country name, the region name, and the type of region, which could potentially determine if that accounts kind of for, let's say, a high average price stations or a budget level fuel station. So as we've prepared now all the attributes data, what we will quickly do to improve the performance for the consecutive steps, we saving all the data to some HANA local temporary tables using the data frame save method, and basically saving those tables now to temporary tables. And it will just take a second. Next, we can again use a more complex SQL statement here, creating our, let's say, station price class data set with all the information we want to finally have and feed into our machine learning algorithm. So the UUID, the brand, postal codes, the geo informations like the geohash hierarchy, the highway distance, and the numerical price indicators, and last but not least, certainly the station class. So that's our input data set. For convenience, we can again use the save method to save that to a HANA table quickly. Maybe we need this multiple times. Typically then for classification and regression is that we again split our data set using a partition method here. So that's our gas station classification base data frame, which we just created. So we saved the data frame to this table and created this data frame. That's what we're using here as input. Then splitting it up into a 70% training set, validation 15%, and test data set 15%. Can quickly do that. And again, then using a new method here, also very popular against the data frame, and that's the describe method, which gives us all the univariate statistical information for each of the columns. Unique values, number of null values. Oh, we have null values for some of the columns, so maybe we want to take care of null values before actually starting the algorithm, or maybe we can do that as part of the machine learning classification model training. We union the train and the validation data set. We want to basically use the training data set to come up with the model, and the validation subset to benchmark the model. How well does the model generalize against data not seen for the model training? Therefore, we have this train validation data frame here. You can see on the right, we have this indicator column as part of the data frame. And finally, we now start to train our hybrid gradient boosting tree classification model here, specifying some parameters, including that imputation for missing value, specifying what's our target column here, which is the station class. That's what we want to model for. And we also specify, okay, we are passing in the data and we're passing in training and validation subsets with that indicator column, which we've just prepared before. And yeah, let's train now that classification model. It will just take another couple of seconds. And now we can use a model report feature, as we specified here, build report true, basically, that all the statistical information is saved to data frames behind the scenes. So we can create this model report, which gives us in a nice condensed format all the statistical information about the classification and the goodness of the classification, as well as some of the charts like the ROC curve, cumulative gains of the model, etc. And what we would be interested here today is the variable importance, as we wanted to see which of the features have basically explaining influence on the actual model we've built to explain the classification. As we can see here now, that the top attributes here are highway distance, the country name has high explainable and decision criteria basically for the classification, our geohash hierarchy feature. So we basically see how important spatial information is for our scenario to determine if a fuel station is in a high price range or class, or in a budget level price class. So that's kind of what we can determine from the statistical output of the respective model. And certainly we could then also apply this model on our test data using the predict method, just as a final kind of demo example, and would then get the respective output here, the station ID, the predicted price classification of a station, the confidence the decision was determined, and then the influencing values explaining the decision. So basically what we refer to as explainability information, so-called SABAs or Shapley value, which we can use here then to see what is the actual influence proportions of each of the values for the stations coming to this classification decision. Okay, and with that, I'd also like to pause here and close the key of the demo. Here in the optional add-on exercises, again, there's some more information about how to score and more model debriefing options, how a model can be stored, and then first and foremost also, if we scroll further down, how you can actually come up with this German highway network information and calculate the spatial distance between the station and the next highway. There's an example given here, basically how to import the highway network for just a small region here near the SAP headquarters, and then how that spatial distance is calculated using a SQL statement here. And the spatial function st distance. So all that's in the appendix here and optional exercise sections for you to explore. And with that, I actually also like to close the demo of the machine learning exercise part, come back to our overall sections, and yeah, can either now take some of the questions or kind of
Christoph, thanks a lot. Let me grab the screen from you for just a second. Okay. So I mean, to all participants, depending on your background, there was tons of stuff that we covered, and you may have felt lost one or the other minute. However, I mean, this is a kind of a workshop. We did all the demonstrations to you, but if you really want to get your hands dirty, I mean, first of all, the session materials are also linked in the workshop description, or you can simply do a Google search for DA180. Again, in that GitHub repository, there is really everything from additional documentation in text down to, yeah, of course, all the code you will also find there. So for example, here you do see the Jupyter notebooks being linked. So these should be ready to run. You find the SQL files if you want to take a look at. And I think that is something, I mean, even if you didn't understand everything, there were certain patterns how to load the data, how to analyze the data that are kind of repetitive and which we see all over in many use cases. So you may very well refer to that GitHub repository as a kind of a repository for code snippets and patterns, which you can get back to if you are kind of facing similar problems like we showed you. Then, right. I mean, just to make sure, I mean, we showed tons of interfaces and tons of tooling. I mean, in the heart of all of that, there is the HANA multimodal capabilities, again, comprising machine learning, full text search, JSON document store, graph, and spatial. These are all native capabilities of the HANA database, and the toolings tap into that, and there are existing integrations, especially also in the spatial area, to GIS toolings, which is used out there in the GIS community. So there are surfaces and touch points, APIs, and how you actually interact with data and capabilities stored in HANA. Then, if you're a TechEd and you want to continue your learning path, prepare for certification, get in contact with other experts, you may want to take a look at that website that is linked here, learning.sap.com/TechEd, in order to learn about additional offers for participants of that. Now, one last thing. As I said, all the code is in the GitHub repository, and if you want to get your hands dirty, most of the exercises do run on the SAP HANA Cloud trial instance, which is there, and you can provision yourself for free. However, if you really want to do some additional stuff, which is not covered by the SAP HANA Cloud trial version, shoot us an email. We will keep the system that we used for the demo alive for a couple of more days. So if you want to use our systems, we can provide a user to you and you can run the exercises yourself. Okay. That's it. We are already on the top of the hour. It was, I hope it was fun 2 hours for you and you took away something. Don't know how to provide feedback, but there should be part of the actual TechEd application. So please shoot us some feedback or some suggestions, what you liked, what you didn't like, so we can improve. And with that, many thanks for your time. Bye-bye.
Many thanks. Bye-bye from my side.